The 3D three-dimensional imaging in biological cell is very crucial in investigating in the cell biology. It provides a lot of insight about the dynamic of the cells, and 3D dimension already have been invented in a couple of years, including a lot of techniques like the convolutional microscopy. One of those is I can call the optical diffraction tomography. There is a lot of advance in optical diffraction tomography because it doesn't yield the agents or dye, and it can provide the 3D dimensions of the refraction index, and the cost is really low because it uses the visible light instead of using like very high expensive like the X-rays. For the setup, like it have multiple configurations. So, for example, if I can have a cell in the middle and I can side in, I can illuminate the cell by have the multiple angle of the beam, and I scan the sample. And in order to rotate in the beam, I can have a lot like 3 different kind of configuration by using the gyro mirror, using the spatial light modulations, or use the digital micrometer device to rotate the beam hitting the cells. Also, I can rotate the cell or scanning the cell back and forward to the focus plane. By doing that way, I have a multiple electrical field of the cell based on a different illumination angle. From that, I can reconstruct the 3D dimensions, internal 3D dimension of the cell. So from the one access, by hitting the sample with multiple direction, I have multiple electrical field around the sample, and I start 2D the diffraction image into the 3D Fourier space, and using the algorithm constraint algorithm to reconstruct back the 3D diffraction index. So this is the electrical field, and this is the intensity, and this is the phase. This is the complex electrical field, and the intensity can be detected by the camera. But however, in order to get the phase of the field, I have to use another technique. It's called the phase retrieve technique. Like here, I can use the intensity equations, transport intensity equation, or subtle light illuminations, or using the digital holographic microscopy to retrieve the phase here. So I do 2 experiments on this one. I use the DCNN to reconstruct from the intensity image to the phase because I want to get rid of it. This part it requires a lot of optical setup. It could be very complicated. And for another experiment, I use multiple intensity around the sample to reconstruct the 3D dimension instead of using the phase retrieve techniques also. Briefly about the phase retrieve techniques, I want to introduce. First one is the transport intensity equation of the TIE. The TIE is a technique using multiple images in the axial direction, at least 2, to reconstruct the phase of the object here. So for example, because in the equation I have to measure the gradient of the intensity changing in the x direction. So I have to capture the image at this distance and another distance. So for example, this is the first distance and another distance. This is the gradient changes, and after apply for the formula to reconstruct the phase, and I do it coupled to the diamond sphere, and applies on the biomedical imaging within the cell, and I can reconstruct the phase. Remember, this is only the phase imaging. For another technique to get the phase, I use the digital holographic microscopy. This technique requires only the one source instead of using multiple sources like the TIE, but it requires another setup by using by set up another reference beam. This technique take advantage on the interferometer on the CCD to the on the CCD on the CCD and use the Fourier transform to detect the virtual image. From that, I can calculate the phase aberrations. In here, I use the CNN to do the segmentation and compensate the phase of the background, and then finally I ungroup it into to the final phase. So from this technique and the previous techniques, the setup would be very complicated. But I don't want to have to measure the multiple images or use the reference beam like this one. So I want to introduce a technique using the convolutional neural networks. It can be learning directly from one image here to reconvert the phase image here. This is one of experiment I want to talk about. So from another experiment, when I had a multiple intensity diffractive intensity, I also reconstruct the 3D dimensions. So there is two experiment I would like to introduce. So what is the convolutional neural network? That is the setup of the multiple layer in the middle from the input and output, and it can be extract the feature from the image, and it will reproduce the output based on what we have here. For this application, it is for the classifications. I want to reconstruct the image. This is the car, truck, or the bicycle. And during the time of training, I can train the model to distinguish the image, what type of this image. And another application of the convolutional neural network, we also do the segmentation. It understands where is the car, where is the road, where is the sky, and do the segmentation in the image. And also it can have a lot of application on another object like the animal, background, the bicycle, the people. Also, deep learning can do to enhance the super resolution by using the regular image or using in the biomedical sample also. So there is a lot of application here. So in here, I want to use the deep learning to understand the diffraction, understand the intensity image and convert it into the phase, instead of using the phase retrieve algorithm that I just introduced. And the second, I use the multiple intensity image and I reconstruct the 3D refraction in that. So for the first setups, I create the phase image and I put it on the SLM, and I let the light go to hit the beam splitter and hit back to the SLM. In here, the light going to be changed based on the phase of the object I put on in the SLM, and it go back into the CCD camera. From the CCD camera here, I capture the diffractive intensity image, and I use this one for the input, and I use the image I put into the SLM spatial line modulations to be the my growth tool, and I use the unit model to train. From here, I train from intensity and I convert it into the phase, and in the results I have here for the diffraction image. I convert into the phase, and it is the growth tool, and it is comparisons between two images. So from 2D, this is for 2D training, and then I move on into the 3D training. In the 3D training, the problem we have here, we don't have enough data, so I can create the data by my own. I create a lot of the volume with the 3D diffraction index, and I create this kind of phantom in different size, different location, different location and different angle, and I create around 400 of it, and I put because it is the 3D object and the SFMC only have a 2D display. So I calculate the phase out of it by assuming the light from here go into the sample, and it's gonna be create the 2D phase, and I put 2D phase, and I put this 2D phase onto the SFM that in the first experience, and I let the light propagate into the CCD camera, and I capture the diffraction image here. So from this image, I can rotate this object. Of course, I cannot rotate the real object physically, but I can rotate the volume matrix of it, and I calculate the corresponding phase. And so in the end, the intensity image is going to be changed corresponding to it. After capture the intensity image, I do some kind of the processing because the setup is not so perfect, so it's not really aligned. So I have to do registrations for both, and I subtract the background, and I keep only the diffraction pattern. So when I rotate 360 degrees, I have like 360 2D image, and I stack it into the 3D volume like this one. This one for the first slide, and this is the raw image I capture from the camera. And I do some pre-process by using the inverse radiance transform to convert the x, y, theta, which is the rotation angle, into x, y, and z. We have the 3D dimension physically. So this is the final step after I fit in the data into the model. And the model is the 3D dimension using the 3D convolutional neural network to reconstruct the 3D diffraction index. So and in here I kept like 40 volume intensity, 40 diffraction index volume at the testing, and I use the rest for training. So this is for the training process. If I here is the plot of the training, it goes down conversion very well. If I use the inverse radiance transform, if not, the training is still okay, but into the validation it's not really okay. And here I use the inverse radiance transform with and without augmentation to create more data. The augmentation is to rotate, change different angle of the volume to create more general feature for training. And this is for some kind of it's not really huge, but it have a little bit improved. So this is for the testing using the mean square error from the label and the volume that I predict from the model. And this is not using the inverse radiance transform, and the red one is using the inverse radiance transform, and the yellow ones is inverse radiance transform and augmentation. And this is for the final results. So this is the gradual what I created before, and this is the one I predict using the 3D convolutional network. And this is I predict it not quite good because I didn't use the inverse radiance transform. This is 2 sample out of 20 sample in the testing data. And this is for the rendering 2D rendering for the first epoch. Which is I beginning of the training, and after training I can reconstruct the internal structure of the sample, and even the diffraction index quite close to the gradual. Yes. So that's for recap. Yeah, in here I didn't use any phase. I didn't use any phase retrieve algorithm, which is very crucial in the ODT. In here I just only use the intensity image to reconstruct this visual. And for the next step, I want to apply this one into the cell, but But to be able to do that, I have to have a lot of ground truth, which I can set up a real ODT to reconstruct the 2D reflection and use that for the label, and I can train for the same procedure here to reconstruct the 2D reflection index. Yeah, I think this is the end of my slide. And any question?